Colin's going to give us a brief, well, as brief as Colin can be, but until our break, he's going to talk to you about how to build a UFO detector for all you enthusiasts who might like to do so. So I'm just going to bring up some slides that he's given us. Here you go, Colin.
Even back in the early days, people recorded that compass needles ran wild when UFOs were nearby. So obviously they do disturb the Earth's magnetic field quite seriously, and on that principle it's not too difficult to build quite simple equipment that, you know, almost a 12 and 13-year-old kid could build. So I'll give you a brief rundown, and then if anyone's interested, I've got printouts of the circuits and things like that. Now, you can act, in fact my brother-in-law made and sold lots of these. These are the UFO detector that you can carry around. I find them a little unstable, but just to prove that it works, this is a very powerful magnet. Put the magnet over there, switch this on. UFO comes near. Of course, that's not very helpful. You can actually take it a step further, obviously, and that's what our circuits will do for you. But don't get put off by the fact that I'm talking about things. Your washing machine, your car has got all of these things inside it, so it's not high-tech stuff. As you can see, this is the Earth here, with its force fields extending all the way out. Next. I'm going to shoot through this, just to get you an idea of the feeling of what we are. Even if you're in a boat, you leave waves behind on the water, as indeed we think UFOs do the same thing. So even after the UFO has gone, the Earth's magnetic field is still going to be swinging around and disturbed. Next. So there's another diagram of the Earth's magnetic field, and you can see we've got a compass in the middle here, which aligns north and south. Okay. Next. UFOs can come and they make waves in the gravitational tube. Next. So instead of having all nice straight lines, after the UFO has gone through, we're going to have all these wizzy-wazzy lines that are going to take some time to settle down. Next. That's a standard navigational compass. As you know, normally ones in ships are dampened by being in a liquid, but this one is much more unstable. I actually tried to build my first UFO detector using one of these. Next. As you can see, the bar magnet disturbs the field, but with gold plating and all sorts of mucking around, testing it with the magnet, it didn't work. It was intermittent. Now we're talking about doing a big fishing trip here. I mean, I had my UFO detector running, I think it must have been about 10, 12 years non-stop. It never failed. I tested it weekly. Well, I didn't expect to get a bite. I mean, this is a really big fishing trip. So you've got to make sure that your bait is good and your rod and all your equipment's fully functional all the time. Otherwise, that one bite and you'll miss it. Next. Here we have an ordinary bar magnet and surrounded by lots of compasses. See how all these compasses are once again reinforcing that powerful force field that goes around just an ordinary bar magnet. Next. This is the machine that I made. It looks a bit cumbersome, but it's very technical, but simple to make. So what we're looking at here is a plastic aquarium. We'll show you the business end here, suspended from a wire. Everything's made of plastic or brass, so it won't be affected by magnetism. Suspended on a wire in here is a magnet, an ordinary bar magnet, such as this. In fact, it was identical to that. Extended by this red needle, which is actually only made of balsa wood. Took a lot of making and carving because I didn't want anything that was going to have too much mass. And the idea of having this needle is the smallest movement here is going to be a big movement at the other end. Okay. In here is a block of concrete, no steel in it. The wall behind, better blocks, no steel in it. Over the top of this, there's a big fiberglass container, which we took off so that we could take a photograph. So everything is hermetically sealed, so that ants can't get in it, no moisture. This bag here is full of silica gel to keep the moisture levels down. The cables go through the bolts at this end. Okay, so this is now looking at it from the other end. So we've got the hold down bolts here. These are fully adjustable. Between these two, with power coming up here, power coming up here, between these two here, we've got an LED, right, running on 12 volts, running continually all the time. You can just see the needle heading this way, okay, and the needle, on the tip of the needle, underneath here, is a little bit of plastic, and down here is a light gate. See, there's a little groove between these two plates, and the LED shines through this tube, so that when that needle deviates the slightest bit, the light from this LED will now go down, and built in here is a light dependent resistor. Okay, next. So there's a bit more of a design for you to show you what's happening. The only thing is that when I drew this, I forgot when I built it, I made it slightly different, but still the same principle, except that the light gate really is between here and there, but that doesn't matter, the same result's going to. So here's your light dependent resistor. So as soon as this deviates the slightest bit, the light will go through, and the light dependent resistor then sends a signal to all your circuits. Now I did find that with very careful tuning, I could get this within a half a degree. If you move it, if you have the accuracy, the sensitivity, I should say, more than a half a degree, that seems to be the variation in the Earth's magnetic field naturally, so you'll get false alarms. It wouldn't be impossible for anyone who wanted to spend the money to have a series of these interconnected, so that you've got to get 4 or 5 clicking off to prove that something's happened. Next. Okay, there's the circuits. Noel Barron, who gave me these circuits, he actually used to attend the meetings very often many years ago. It's fairly simple. We've only got one transistor, light dependent resistor. I didn't come up too well, did they? Well, that's a relay. So the coil of the relay is 12 volts via the magnet. All these gizmos here in that circuitry. We now trigger these relays, which, as you know, with relays you can have them normally on, normally off, or you can have them self-locking, or the relay can actually supply another relay which has got a timer on it. Next. So once you've got that signal from this light dependent resistor, so the power goes in here, stops. Once you put light on this circuit, the power then flows through it. So common stuff. You've all walked through these many times because they're often operating automatic doors, right? So you break the beam, the signal goes through to there, and the door opens, if you're lucky. These are light emitting diodes. In those days you only had red ones. I can't offer any opinion as whether other colours would be better or not, but I just used a red one. As you know, these diodes use practically no electricity. In fact, the first one was indeed a stone. A guy found that if you put a current on a stone it would glow, so we refined it for that. And most of our house lighting there is moving towards this because it's a smooth light and it doesn't drag much current. Next. A better view of this little set of relays. They do come with a base if you want to be sophisticated. You just poke your wires in there, read it off and muck about, and as I say, you can get a UFO to blow up the City Hall if you wanted to. I mean, it's all a matter of once you've got that signal, there's nothing you can't do. Next is a switch that under control of another circuit, so you can get that impulses, and you can latch it, so you can bring the circuit back round onto itself so that it stays on until you press a button and turn it off. And as you know, when you open your fridge door, the light comes on, doesn't it? That's because that's operating on a normally off button. So when you open the fridge, it comes on, but normally when you shut the door, it goes off. So you can do what you like, really. Next. Then, of course, we're internet wanting to make a recording. We've got an event happening here, let's hope, and we want to record it. Well, you can have a pinhole camera, which is a simple device, namely, it's looking at the whole sky, because we don't know where this thing might be. So a pinhole camera will look at the whole sky. Okay, so we're going to switch it on. Next. Or we can have something a bit more sophisticated. One of the wonderful things is that our technology has advanced so rapidly, there's heaps of second-hand stuff out there that nobody wants that still works. Okay, I mean, I've got a really beautiful camera, it's thousands of dollars worth, but it takes normal film. So I've got a loader sitting in my lounge ready to take a picture through the window if I need. I mean, it's not an investment because you can't sell it, even though it does a good job. Okay, next. And you have microphones. I had mine set up with a microphone outside the building and one inside the building, so that when it was triggered, 2 tape recorders started to run and the clock stopped, so we knew what the time was when the event took place. Next. You can have flashing lights to alert you. I actually had car horns. If you go to wrecking yards, they go, more blinking car horns. The most reliable part of a motor car is the car horns. You can buy heaps of it, you know, you can make yourself deaf with them. Because I lived and worked in the same location, I could hear it half a kilometre away when it went off. I mean, it never went off with a UFO, but I did test it regularly with a magnet. Okay, so we've got even more sophisticated. You can buy these really cheap phones now. And you could have it so that that cheap phone, if the detector went off, it would send a signal to your phone. Anywhere on the planet. Or to all your friends' phones, all the members of the club. And as I say, you can have sirens. And when I was on the internet looking, I googled siren, I got more than I bargained for.
Thanks, Colin.